The experiment is making some nervous that it could create a cosmic black hole.
There is a tunnel and machinery inside that tunnel.
Particle accelerator altered the weight of one electron and therefore destroyed our universe.
Our understanding of reality is just beginning to unfold. As we delve into the unknown, we reveal astonishing secrets, such as boundless energy, a shared consciousness, remarkable human abilities, and concealed dimensions. The world's most advanced high-energy particle collider has been long awaited by global physicists, eager to revolutionize our perception of the cosmos. After a protracted construction period, CERN unveiled the Large Hadron Collider, LHC, in September 2008, with its creators perfecting the machine over several more years. Since its inception, the LHC has shed light on numerous cosmic riddles during its various runs. Yet, when the energy beam of the LHC was recently pushed to its maximum capacity, CERN scientists stumbled upon an unforeseen and disquieting discovery. The cause remains uncertain, with only conjectural explanations offered thus far.
This is the equation come to life. This is what I love about it.
Built between 1998 and 2008 in collaboration with over 10,000 scientists and hundreds of universities and labs from more than 100 countries, the LHC sits within a 27-kilometer tunnel, approximately 175 meters below the France-Switzerland border near Geneva. In 2010, the first collisions achieved an unprecedented 3.5 tera-electron volts per beam, and subsequent upgrades pushed the energy level to 6.5 tera-electron volts. The collider, equipped with 4 crossing points where accelerated particles collide and 7 detectors designed to observe various phenomena, primarily accelerates proton beams, but can also propel heavy ions like lead. Lead-lead and proton-lead collisions typically take place for 1 month per year, further unveiling the enigmatic nature of our universe. Enshrouded in mystery, the collider's primary purpose is to allow physicists to delve into the enigmatic realm of particle physics theories. They seek to unravel the enigma of the Higgs Boson's properties and uncover the elusive family of particles foretold by supersymmetric theories. The word hadron alludes to subatomic composite particles, bound by the formidable strong force, much like atoms and molecules held captive by the electromagnetic force. Known hadrons encompass baryons, such as protons and neutrons, and mesons like pions and kaons, first revealed in cosmic ray experiments during the twilight of the 1940s and dawn of the 1950s. A collider, a distinct breed of particle accelerator, merges 2 opposing particle beams, instigating a cascade of collisions. Though formidable to construct, colliders serve as potent instruments in the quest to understand particle physics, attaining far greater center of mass energies than their fixed target counterparts. Scientists scrutinize the remnants of these collisions, seeking revelations about the subatomic realm's architecture and the enigmatic laws that govern it. Many of these ephemeral byproducts can only be conjured through high-energy collisions, vanishing rapidly and eluding alternative methods of study. The collider resides within a sinuous tunnel, its depths ranging from 50 to 175 meters below the surface. This intentional variation in depth allowed tunnelers to skirt the Jura Mountains, circumventing the excavation of a vertical access shaft. Within the shadowy depths, a particular tunnel was selected to spare CERN considerable surface land expenditures and avert any lasting impact on the landscape. The embrace of the Earth's crust provides sanctuary against the ever-present background radiation. The 3 8-meter-wide tunnel, clad in concrete, was constructed between the years 1983 and 1988, previously housing the enigmatic Large Electron-Positron Collider. The tunnel transcends the border between Switzerland and France at 4 junctures, predominantly lying beneath French soil. Above ground, auxiliary structures house vital equipment such as compressors, ventilation systems, control electronics, and refrigeration units. The LHC, alongside LHC-related simulations, begets approximately 15 petabytes of data annually. A computing grid, birthed from the LHC project, was conceived to manage the immense data harvest gleaned from the myriad of collisions. This grid represents an international alliance of grid-based computing network infrastructure, With an estimated cost of 7.5 billion euros, the Large Hadron Collider stands as one of the most costly scientific instruments ever forged. Its construction, sanctioned in 1995, was allocated a budget of 2.6 billion euros, with an additional 210 million euros designated for experiments. The LHC began its enigmatic operations on September 10, 2008. An unforeseen magnet quench incident delayed initial testing for 14 months, resulting in extensive damage to over 50 superconducting magnets, their mountings, and the vacuum pipe. During the first run from 2010 to 2013, the LHC orchestrated collisions between two opposing particle beams composed of either protons, up to 4 tera-electron volts, or lead nuclei. Discoveries unearthed in this first run encompassed the elusive Higgs Boson, a plethora of composite particles like the bottomonium state, and the inaugural creation of quark-gluon plasma. The primary research objective of the Large Hadron Collider was to probe the potential existence of the Higgs Boson, a vital component of the Standard Model of Physics, whose presence had been theorized but remained concealed due to its immense mass and enigmatic nature. Cloaked in enigma, researchers conjectured that if the Standard Model held true, the LHC would spawn numerous Higgs bosons every minute, allowing physicists to definitively affirm or refute the existence of the Higgs boson. Moreover, the Large Hadron Collider granted scientists the means to seek out supersymmetric particles and other hypothetical entities. Following preliminary tests in 2008, the inaugural operational run transpired from 2009 to 2013, succeeded by a protracted shutdown for enhancements until 2015. The second operational run unfolded from 2015 to 2018, giving way to yet another extensive shutdown until 2022. In April 2022, the LHC recommenced operations with a heightened maximum beam energy of 6.8 TeV. This run is predicted to endure until 2026. During the third run of the Large Hadron Collider, scientists were confounded by the emergence of a fracture in Earth's magnetic field on the 7th of July. Unlike a fleeting lightning bolt, this enigmatic fissure persisted for an astounding 14 hours. Forceful solar winds surged through the aperture, igniting colossal geomagnetic storms and birthing awe-inspiring auroras. Devotees of science fiction were enthralled by this news, with some conjecturing that perhaps a nefarious behemoth from Stranger Things had infiltrated our realm through the rift. Alas, this is merely a fervent fan's reverie. The geomagnetic tempest birthed by the fracture did yield auroras of such mesmerizing allure that it proved challenging to avert one's gaze. Yet the question remains, what caused this fracture to materialize? It appears the chasm in the magnetic field was forged by an uncommon celestial event known as a co-rotating interaction region, CIR, emanating from the Sun. CIRs are vast plasma formations birthed in the low to middle latitude realms of the heliosphere, where swift and languid streams of solar wind intertwine. The heliosphere, a domain encircling the Sun, encompasses its solar magnetic field and solar winds. Bearing resemblance to coronal mass ejections, CMEs, interaction regions are unleashed from the Sun towards Earth, carrying shockwaves and dense magnetic fields that conjure tempestuous space weather, often materializing as resplendent auroras. This particular celestial event assailed Earth's magnetosphere in the early hours of July 7th, inciting a persistent G1 class geomagnetic storm. National Oceanic and Atmospheric Administration, NOAA, analysts posit that the coronal mass ejection was nestled within the solar wind preceding the co-rotating interaction region. But does this fracture portend calamity? Authorities reassure that the phenomenon is not cause for alarm, as fissures in Earth's magnetic field are relatively commonplace. The magnetic field serves as a bastion shielding us from solar storms unleashed by the Sun. It is surmised that myriad cracks in the field open and seal fleetingly. However, these recent fractures have revealed their capacity to linger for several hours. Harold Frey, the principal author of a 2003 study unveiling this discovery, likened the circumstance to a drafty house with a window obstinately ajar amid a tempest. The house repels the brunt of the storm, but the couch is ravaged. Analogously, our magnetic shield endures the onslaught of celestial storms, yet some energy permeates the fissures, sporadically causing complications for satellites, radio communications, and power systems. Fortuitously, the fracture in the magnetic field did not precipitate radio blackouts or power failures. Instead, inhabitants of Canada and the US were graced with mesmerizing northern lights displays. Scientists have observed that the Sun approaches the zenith of its activity within the solar cycle, occurring sooner than anticipated. Consequently, the likelihood of witnessing an aurora remains high and is expected to increase over the next 3 years. The enigmatic Large Hadron Collider, LHC, has revealed more than mere fissures in Earth's magnetic field. In July 2017, examinations of data gathered in 2016 were unveiled, providing a deeper understanding of the Higgs boson's properties and refining the precision of other discoveries. Since March 2021, the LHC experiments have unearthed approximately 59 new hadrons. On July 5, 2022, analysis of data from the collider's initial 2 runs reported the sighting of an unprecedented pentaquark composed of a charm quark, a charm antiquark, and up, down, and strange quarks during the decay of a charged B meson. Particle physics experiments often encounter waning returns after several years of operation, as the primary outcomes attainable by the device are accomplished, and fewer results emerge in subsequent years. A solution to this challenge lies in the enhancement of the devices involved, such as amplified collision energy, luminosity, and refined detectors. In June 2018, an upgrade to the Large Hadron Collider, dubbed the High Luminosity Large Hadron Collider, was initiated, striving to augment the accelerator's potential for novel discoveries commencing in 2027. This enhancement aims to amplify the apparatus's luminosity, elevating the odds of observing elusive processes and refining statistically borderline measurements. The LHC's 3rd run is deemed an intermediate phase in the collider's agenda. The first run's crowning achievement was the unearthing of the long-awaited Higgs boson. The second run's notable accomplishments encompassed the revelations of significant decay modes of the Higgs boson, substantiating this particle as the source of mass for weightier known elementary particles. CERN envisions the new 3rd run, slated to culminate in late 2025, to double the current LHC dataset. This 3rd run will likely be succeeded by a more extended preparatory period, potentially spanning through 2029. The thoroughly upgraded LHC is then projected to recommence operation, 10 times greater than the existing one. The 4th run is estimated to endure until 2042, generating a dataset nearly 10 times larger than the one anticipated at the 3rd run's conclusion. Crucial to LHC physics is the amassment of colossal volumes of documented proton-proton collisions for examination. Protons are selected for their ease of handling and manipulation, facilitating acceleration to the utmost energies. Nevertheless, protons are not elementary particles. They are bound states of quarks tethered by gluons, particles constituting the strong nuclear force. To better grasp collisions at the LHC, envision a proton as a sack of jelly beans containing quarks, gluons, antiquarks, and heftier particles such as W and Z bosons, the weak interaction quanta accountable for radioactive decay. As 2 protons collide, it is as if 2 sacks of mystical beans are torn asunder, spilling particles that reassemble into protons, pions, kaons, and other familiar entities. On rare occasions, a mere pair of quarks or gluons collide headlong, condensing their energy into an infinitesimal point before releasing it back into quarks, gluons, or perhaps even weightier known and enigmatic particles. By scrutinizing these exceptionally scarce reactions resulting in tremendous energy liberation, physicists can delve into the laws governing nature at unimaginably minute distances. As the Large Hadron Collider amasses more data, the rare reaction samples will multiply, augmenting the prospects of unveiling momentous discoveries. Detecting these sporadic high-energy collisions poses a formidable data conundrum. Proton bunches clash 40 million times per second within the LHC, with each bunch collision encompassing at least 50 or more individual proton-proton collisions. The LHC's principal detectors, ATLAS and CMS, seize photographic traces of these collisions, which are subsequently committed to permanent storage. Each image is nearly 20 times larger than an average smartphone photo, signifying that storing evidence for just 1 second of operation would generate a colossal million-gigabyte archive. Alas, the majority of the 40 million events per second are simple and familiar ones, with merely a few thousand W boson events and a lone Higgs boson event concealed within the data stream. One vital component of each LHC experiment is the trigger, a compilation of computer processors that cherry-pick a few hundred collisions per second for permanent documentation and subsequent dissection by physicists. In the midst of a vastly selective endeavor, the LHC experiments have already birthed one of the largest computer databases known to mankind. The primary quest of the LHC now lies in uncovering new elementary particles that could bear witness to hitherto unknown fundamental interactions. Some of these proposed particles could be hefty, decaying into clusters of quarks and leptons exhibiting exceptional energy. Yet, do not be misled into believing such particles will be unveiled during Run 3. At most, these experiments might yield intriguing statistical hints and perhaps suggestive event imagery with novel attributes. This will undoubtedly set the theorists' tongues wagging. The high-luminosity Large Hadron Collider in Run 4 and subsequent runs are anticipated to corroborate these insinuations. At present, a genuine opportunity lies in the search for weakly coupled new particles, akin to those predicted in models of dark matter reactions. The production of such particles tends to be scarce, as they are not forged by strong interactions, but rather by weak electromagnetic ones. Hence, any enlargement in the dataset could prove advantageous. The elusive dark matter particle interacts far too weakly to leave a trace in the Large Hadron Collider detectors. However, this is not a hindrance, as one can observe visible particles recoiling against the unseen emissions in accordance with Newton's third law. In numerous models, the partners of dark matter particles emit trifling amounts of visible energy, leading to minimal recoil signals that elude the experiment's triggers. Run 3's trigger enhancements are predicted to refine the coverage for such faint signals, and the heightened rate will aid in procuring a sample of rarer events, wherein recoiling particles are propelled into clearer view. This improvement will vastly augment ATLAS and CMS's capacity to discern these signals, but that is not the end. CERN also harbors multiple preliminary designs for a future circular collider, poised to be the most formidable particle smasher ever constructed, with an estimated cost ranging from 9 to 21 billion euros. Yet not everyone is persuaded that the future circular collider is a wise investment. Sabine Hassenfeld, a theoretical physicist at the Frankfurt Institute for Advanced Studies in Germany, contends that there is no justification for believing new physics will emerge in the energy realm that such a collider would access. The colossal funds required could be more judiciously allocated to other grand facilities, such as situating a major radio telescope on the moon's far side or launching a gravitational wave detector into orbit. Both ventures would be sounder bets than a new collider, especially considering the LHC has yet to conclude its third run and prepare for a fourth, both of which will contribute more than sufficiently to particle physics for now. Like all grand scientific endeavors, the LHC advances at a deliberate pace, simultaneously granting us access to deeply concealed knowledge that was once unattainable. Run 3 marks the next phase of this journey, and physicists eagerly anticipate the unveiling of numerous surprises, akin to the recent enigmatic fissure in Earth's magnetic field that persisted for several hours. Amidst the remarkably discerning approach, the LHC experiments have already become one of the most extensive computer databases worldwide. The primary aim of the LHC now is to unearth new elementary particles that might provide evidence for yet undiscovered fundamental interactions. Some of these proposed particles could be massive and decay into clusters of quarks and leptons with exceedingly high energy. However, it's improbable that any such particle will be found in Run 3. At most, these experiments might yield captivating statistical hints and potentially suggestive event images with novel features, sparking discourse among theorists. The high-luminosity Large Hadron Collider in Run 4 and subsequent runs are expected to substantiate these insinuations. Presently, a genuine opportunity lies in the search for weakly coupled new particles, akin to those predicted in models of dark matter reactions. Generating such particles usually occurs at low rates, as they are not the product of strong interactions, but rather weak electromagnetic ones. Consequently, any expansion in the dataset could be advantageous. Dark matter particles interact too weakly to leave a signal in the Large Hadron Collider detectors. However, this is not a concern, as one can examine visible particles recoiling against the invisible emissions in line with Newton's third law. Yet, in many models, the partners of dark matter particles emit minimal visible energy, resulting in scarcely perceptible recoil signals that evade the experiment's triggers. Run 3's trigger enhancements are anticipated to improve the coverage for such faint signals, and the heightened rate will aid in obtaining a sample of rarer events where recoiling particles are more readily visible. This refinement will considerably augment ATLAS and CMS's capacity to identify these signals, and that's not all. CERN also harbors several preliminary designs for a future circular collider, poised to be the mightiest particle smasher ever constructed, with estimated construction costs ranging from 9 to 21 billion euros. However, not everyone is persuaded that the future circular collider is a sound investment. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies in Germany, has asserted that there is no basis for believing new physics would emerge within the energy scope that such a collider would access. The substantial funds could be more judiciously allocated to other grand facilities, such as situating a major radio telescope on the Moon's far side or launching a gravitational wave detector into orbit. Both alternatives would be more reliable bets than a new collider, especially considering the LHC has yet to conclude its third run and gear up for a fourth, both of which will contribute considerably to particle physics for the time being. Like all significant scientific endeavors, the LHC advances steadily, simultaneously granting us access to deeply concealed knowledge that was once unattainable. Run 3 marks the next phase in this journey, and physicists eagerly anticipate the unveiling of numerous surprises, akin to the recent enigmatic fissure in Earth's magnetic field that persisted for several hours. In addition to delving into these newfound revelations, LHC researchers also aim to probe further into other enigmas, encompassing the particles that constitute dark matter, the theory of supersymmetry, and axions, to mention a few. Physicists are optimistic that the reinitiation of collider experiments will empower them to address lingering questions about the cosmos, fostering new discoveries and breakthroughs in the realm of cosmological research. What secrets await us? Only time will divulge the answers. We'd love to hear your thoughts. Share your opinions in the comments section below. And don't forget to subscribe to our channel, for together we'll embark on this extraordinary journey of exploration alongside you.